So we're looking at VK Mini Path Tracer. So this is a relatively small, beginner-friendly path tracing tutorial. Tutorial is introduction to writing your own fast, photorealistic path tracer in less than 300 lines of C++ code and 250 of GLSL shader code. Here's an example of what you'll get at the end of this tutorial. Vulkan is a low-level API for GPU programming. Works on a wide variety of platforms, from workstations, gaming consoles, tablets, mobile phones, to edge devices. Vulkan is usually known as a complex API, but I believe that when presented the right way, it's possible to make learning Vulkan accessible to people of all skill levels, whether they've never programmed graphics before or whether they're a seasoned rendering engineer. Perhaps surprisingly, one of the best ways to introduce Vulkan may be with GPU path tracing because the API involved is relatively small. I'll show how to write a small path tracer along with the NVVK helpers included in the NVPro samples framework to help with some Vulkan calls when needed. For advanced readers, we'll also optionally talk about performance tips and some implementation details inside of the helpers and Vulkan itself. Final program uses less than 300 lines of C++ and 250 of GLSL, including comments. Find that there. Look at that later. With some Vulkan functions used in the main tutorial. Allocating command buffers, beginning command buffers, binding command. Yeah, all right. The whole 9 yards. Right, cool. Everything to do with descriptors, command buffers, pipelines, all that stuff. Supported GPUs works with all GPUs that support ray queries as time of writing. This is all GPUs with hardware accelerated ray tracing. Series cards don't support ray queries, but they do support ray tracing pipelines. Okay. RTX GPUs have RT cores, dedicated hardware units make acceleration, structure traversal, and ray triangle intersections much faster. Older GPUs also emulate some kinds of ray tracing. Older NVIDIA GPUs can also perform ray tracing using OptiX. OptiX 7 is relatively close API to the Vulkan ray tracing API. Tutorial uses ray queries because they reduce the amount of C++ code by about 75 lines. But ray tracing pipelines let shaders call other shaders. Can be faster in multi-material scenes. In the box in section 6.1, there's more information about trade-offs between ray queries and ray tracing pipelines. If you have a GPU that supports ray tracing pipelines but not ray queries, you can still use. There's still many ways to learn Vulkan and ray tracing. If you don't have prior Vulkan experience, you can follow this tutorial to chapter 8. Skip 2.3. And then just look at the ray tracing pipelines chapter. If you've done Vulkan before, you can look at the NVIDIA Vulkan ray tracing tutorials, which will work on your GPU. Go into more detail about ray tracing pipelines than this tutorial. And there's more useful Vulkan and ray tracing tutorials. At the end of each chapter, there's a program you can run. In addition, including versions of the project at the end of each chapter, you can compute a file comparison between your project and the reference project. See see if you've made any typos copying the code. Some sort of diff tool. More different tutorials. We've got let's say a tutorial for programmers of all skill levels. There's a bunch of different ones available for different skill levels. Particularly if you've already have experience with rasterization or Vulkan, or already have a rendering engine that you'd like to use ray tracing for, you may want to look at the NVIDIA Vulkan ray tracing tutorial. Some other tutorials might be helpful in combination with this Vulkan tutorial about rasterization. Alan Wolf has his casual shader toy path tracing series. Speaking of, this is actually really cool. I want to mention this while I'm thinking of it because it came up. This Alan Wolf's.
You have the power to change lives, starting with your own.
Alan Wolf had that thing about the defocus blur thing, using the different aperture shapes. This guy made a camera little shim thing out of an LCD, which is yeah, let me just find what it actually looks like. So it's a little LCD panel that goes in front, and it acts like a shutter. And it was really interesting because yeah, anyway, this is what made me think of it. Basically, that sorry, a little disorganized.
Maybe let's don't go off topic too much because we are still recording.
Yeah. Yeah. It's anyway, Alan Wolf's thing. Reminded me of that. I'll pull that up later. Ray tracing one weekend. If you're interested in ray tracing on the GPU with CUDA, would be interested in optics. Optics developer forums, NV Pro samples, yeah. For this tutorial, you need 5 things. You need C++ compiler, you need Git, CMake, NVIDIA driver from 2020 or later, Vulkan SDK, preferred way to download the project. Let's use the NV Pro samples build all script. Just cloning this and running the batch file or the shell file. Configuring and building. This is all just set up for their project.
Yeah, I think we can skip that. Like, people can read those on their own if they need to set up.
So we're ready to begin programming with Vulkan. Left as an exercise to the reader. It's so main.cpp and the Vulkan Mini Path Tracer Edit project is starting with this hello world. Helpers for creating a context. Fully functioning program uses Vulkan API. You can run it, will output some interesting information about your GPU and system. Uses subsequent samples to tell the init request different Vulkan features. Okay, so this is like what VK Bootstrap does.
It's a lot high level than VK Bootstrap. It's basically abstract the whole idea of instance, device, Yeah, physical device and device into one context. That's what I did in my own project too. That's how, like, basically in my own project, when I try to follow along, I did almost exactly the same code because but basically it's abstract. It just bundles instance and a device into a single object, and a lot of other stuff probably.
Well, the BK guide does something very similar to it, yeah. Okay, so we got output from this program, reporting some stuff about the GPU and system. In some sense, you can think of Vulkan as a way to use a CPU to program GPUs. When the CPU sends a command to the GPU via Vulkan, many systems the command must pass through to result in an operation on the GPU. One initial abstraction is as follows. An application talks to the Vulkan library, which then talks to the GPU's driver, which sends commands and data over the PCIe bus. When you install a modern GPU driver, you also install a version of Vulkan. It's the shared library, DLL System32 on Windows. So when you initialize a Vulkan instance, it loads and initializes that Vulkan library. One of the most important things about Vulkan is that you can enable additional functionality and features using layers and extensions. Vulkan extensions correspond to different things that your GPU can do beyond core functionality. All information passes through different Vulkan layers before it reaches your GPU driver. For example, you'll notice that the application already uses the VK layer Kronos validation instance layer. It's a helpful layer for debugging. The validation layer keeps track of the current state of all your objects, and whenever you call a Vulkan function, this layer updates its state. Lets one know if anything they've done could violate the Vulkan specification. For example, invalid calls. It also includes object information so they can determine what went wrong. To make debugging easier, one can also add the debug utils extension. We need to assign names to Vulkan objects. It appears in the validation layer's messages, which helps determine which objects are involved. That is a very handy feature. So looking at the validation error messages, allocate command buffers has the following signature. Taking the device command buffer allocation info and the pointer to the BK command buffer and buffers. Vulkan specification for BK allocate command buffer also states device must be valid BK device handle. Allocate info must be a valid pointer to the allocate structure. Command buffers must use a valid pointer to an array of command buffers, or not many of them, and the count must be greater than 0, causing an error with invalid values. Get some stuff from the validation layers. Seen that before. Alright. Physical device and logical device. Important in Vulkan. Two different physical devices, sometimes on GPUs or on laptops, integrated and discrete. Generally, physical devices corresponds to a physical GPU with memory, processing units, and connections to other devices, and the various features it supports. Physical device may also sometimes involve a different driver. GTX 1060 Max Q uses a different driver than the Intel integrated GPU. Logical device usually points to a physical device. When the context creates the device, also specifies a set of device extensions. This is all pretty basic setup stuff. Most important thing are the acceleration structure and ray query, letting you know you can actually support ray tracing on this device. Many GPUs support multiple queues. We don't describe them in detail. We only use one queue for this sample. Submit work to queues. Different queue families support different types of operations. Graphics queue supports graphics operations. Transfer queues for transfer operations. Only use one queue in the queue family, and so this is one that supports all the operations. This chapter went over how to initialize the Vulkan instance, create a physical device and logical device, set up queues. Device extensions and Vulkan objects. Looking at how to specify a version of the Vulkan API for instance creation, requesting device extensions, including the acceleration structure and ray query extensions. You can find out information about the GPU by getting Vulkan features and physical device properties, and create lists of Vulkan objects using PNX chains. If run into any issues, this chapter, you can check the reference code. Make sure you have drivers updated. You set the Vulkan API version. Okay, specifying 1.2. Different ways to initialize Vulkan structures can be tedious.
I think this is basically just C++ membrane, so you can skip.
Yeah, it's a lot of. You've definitely seen this before if you've done any Vulkan stuff. So there's some helpers to make that easier. Device extensions. We need the acceleration structures, we need the ray queries, and we need ray tracing pipelines. So a fallback, I guess, to ray query if you can support it. We're using the ray query because it's faster to get started with. So these two both rely on deferred host operations. All of the other required extensions are included in 1.2. You need to request these three. So what is deferred host operations? We're not using it directly. Allows the driver to run some expensive CPU-based Vulkan API calls asynchronously, such as the Vulkan API call that builds the acceleration structure on the CPU instead of on the GPU, much like launching a thread on C++ to perform a task asynchronously and waiting for it to complete. Note that unlike OpenGL, one can multi-thread Vulkan calls, although one must ensure that two threads don't use the same resource in calls that requires that resource be externally synchronized. And using this extension is not required to do multi-threading. For the deferred host operations extension, we only need to add it as a required device extension. Okay. Some very short and concise names for objects. on call. So creating that S type, yeah. Second argument false. So it's non-optional. This is just part of their device creation stuff. Okay, run the program, see if it works. You can look at the what it gives back if you want to know if it supports it or not. Chapter is about GPU memory, how to read GPU memory back from the CPU. You need to initialize GPU memory allocator. You need to allocate a VK buffer to hold color data. You need to map the uninitialized VK buffer data back to the CPU and print out the first few values. In many ways, discrete GPU works like a second computer. It is extremely good at parallel data processing. It's got its own memory and thousands of cores. However, data transfer is slower than accessing video RAM. It is usually limited by the speed of the PCIe connections between the motherboard and the GPU. CPU-GPU transfers are much higher latency than the direct reads and writes from memory. There's some ballpark figures for the bandwidth involved. Those are fairly high numbers. A good idea to minimize the amount of data transferred between CPU and GPU. Minimize synchronization between the two. For instance, we'll have the geometry back to the GPU and do as much of the computation as possible entirely on the GPU. Yeah, we only get the image data back on the CPU at the end. Applications might also send compressed data to the GPU, which the GPU could either decompress or read without decompressing. It's also a major factor in the design of Vulkan. Instead of potentially sending data between CPU and GPU with every command, Vulkan's design encourages applications to batch collections of operations in command buffers, which are submitted as larger packets of information at once. More ways to send data to the GPU. For instance, the GPU Direct API allows devices like SSDs and network adapters to read and write GPU memory without going through the CPU. Also, Direct Storage API adds NVMe to GPU Direct transfers to DirectX. Vulkan is designed for multi-threaded features. Multi-threaded application can record command buffers on multiple threads, for instance, although it needs to use synchronization techniques like vtexes to avoid resource write hazards. Two threads modifying device state at once. It's also possible to record secondary command buffers and then reuse the secondary command buffers multiple places in primary command buffers. This type of command buffer is what this tutorial works with. For more information about that, there's another article. More headers involved, one for the memory allocator, memory allocation stuff. So we've got malloc implementation. Probably using VMA if you're doing Vulkan stuff. It's the one that a lot of tutorials use. Okay. Visualizing the allocator. So VK buffer is pointer to an array of bytes, like that in C++. Also need to specify what it can be used for with the buffer usage flag bits. So creating a buffer for the image. It's a bunch of floats for the red, green, and blue channels. Eventually using this as a storage buffer. With this buffer's memory to be both host visible and host coherent. This means that although the buffer exists on the GPU, we can read and write on the CPU by mapping it in CPU memory, and some parts of cache management are automatically handled. So creating a buffer. Common pattern is to let a create info struct, then pass the structure to a function that creates the object. This creates, it helps with cases. Objects might have lots of flags and settings. After calling the init on the allocator, compute the size of the buffer and create the buffer. It's the number of bytes. Storage buffer bit and transfer destination bit. Also need the host visible bit, host cached, and host coherent bit. Okay. So make sure to deallocate at the end. You can run the program at this point. Should allocate a 5.7 megabyte buffer on the GPU, then exit. This tutorial uses a VK buffer, store 32-bit floating point image type. Many Vulkan applications use VK images. In contrast to VK buffers, VK images can represent multidimensional data using image arrays and bitmaps, switching between layouts, optimal for different purposes. You can interpolate with samplers and do more different things. Also be drawn to the screen using, there's some functions that are built in for that. VK images are also more complex than VK buffers, so we're skipping this for the main part of the tutorial. It's also unusual to use 3-channel. Doesn't really matter. Retrieving the data from the GPU. Although we haven't written yet, we'll see how to transfer data from the GPU to the CPU. After it's created a buffer, adding the following to map the GPU, map it back on the CPU, then unmap it. So should give the first 3 elements zeros. It's uninitialized data. The use of host visible, host cached, and host coherent. Because it only requires one resource. From the perspective of the CPU performance, the most important factor here is the host cached flag. As without this, the flag will each read of the buffer memory from the CPU must go out to GPU memory and back for incurring extra latency. However, computing on the GPU using device local memory is usually faster. Use a staging buffer. Yeah, I've seen that before in a bunch of different tutorials. So, then it's commands. Creating a command buffer, recording the commands. To fill the buffer with 0.5. So command buffer holds buffer commands. I might think of this as a list of instructions for the GPU. These get submitted to a queue. Need one that has graphics, compute, and transfer. There's more complex setups that are possible. Command buffers contain the commands in order, but they have devices which are designed for parallel execution, so they might not happen in order. Let's get error checking happens with a macro. Okay. A lot more setup stuff for command buffers. Begin the execution. You begin recording and then submit it. Okay, or I guess just recording. Fill the entire buffer with 32 bits, corresponding with 0.5. Okay. Adding a pipeline barrier. Two important aspects of programming in Vulkan. Two commands in sequence does not necessarily mean that the first command will be followed by the second command. They'll start in submission order. They may run in parallel or take turns executing. Unlike C++, running a command that writes to memory doesn't mean that subsequent commands will be able to automatically read those written values from memory except in special cases. In other words, the Vulkan spec notes that happens before is not always sufficient for a write to be visible for a read. To a read, additional availability and visibility operations may be required for writes to be visible to other memory accesses. Basically, you need to avoid specific memory hazards that come from the parallel operation. Pipeline barriers synchronize memory. Also, one type of thing that makes it so that pipeline stages can wait for other pipeline stages' memory accesses and read what those pipeline stages have completed writing. It can be one of the most complex parts of the API, so there's some options. They say basically, make sure that these memory operations finish before the other tasks start. You can visualize it like a physical barrier. So in this case, you just want to make sure that that fill buffer finishes. Do this with VK memory barrier. So creating a pipeline barrier. So specify the pipeline stages. Pipeline barriers synchronize different sets of pipeline stages, which VK command pipeline barrier uses like in the second and third arguments for source and destination masks. Pipeline stage represents a place where data manipulation happens. Two exceptions. They're top of pipe and bottom of pipe pipeline stages. The name pipeline comes from the graphics pipeline. Top of pipe and bottom of pipe represent the start and end of an imaginary pipeline. Okay. For example, there's a pipeline stage for compute shader, pipeline stage for the host, pipeline stage for transfer operations. Also be represented by, or it is represented by VK pipeline stage flag bit mask. Multiple stages can be combined. Source and destination masks essentially say, depending on some details In the barriers, stages in the destination mask will wait for the source mask. Okay, looking at access flags, source access mask, destination access mask. In the barrier are bit masks. A single bit mask represents the way that memory can be accessed. Some examples are transfer write bit, host read bit, and shader write bit. Pipeline stages, the access flag bits can be combined using bitwise OR. In many cases, it's possible to infer pipeline stages from access flags. For instance, VK access transfer write bit is part of the VK pipeline stage transfer bit pipeline stage. Pipeline stages and accesses differ. One of the reasons that pipeline barriers are complex is because they involve both execution dependencies. Operation set A must happen before operation set B, and memory dependencies. One set of memory accesses by operation set A must be made available, and all available memory writes must be made visible. A specified set of memory accesses by operation set B. Pipeline stages are used. Execution dependencies, but both pipeline stages and access scopes are used in memory dependencies. As mentioned above, sets of pipeline stages needed can often be inferred from the combined access scopes. So if they don't synchronize, note that pipeline barriers only synchronize things occurring on the GPU in addition to memory operations within the GPU and involving other systems. Since they're recorded commands in a command buffer submitted later on, they don't prevent the CPU from running further commands, at least in the normal sense. To make the CPU wait for the GPU, we use VK queue wait idle. We could also use VK fences. Unfortunately, queue wait idle isn't guaranteed to be enough to make memory writes from the GPU correctly accessible by the CPU. See in the last text box in this section has full explanation. However, the reverse, where making memory writes by the CPU accessible by the GPU, often doesn't require a pipeline barrier. According to section 6.9 for host write ordering guarantees. At this point in the programming, the GPU is waiting for the CPU to submit work, and CPU is recording a command buffer. Yeah. We're kind of abusing the information box element here. So there's different types of barriers that you can supply to VK command pipeline barrier. Memory barriers say create a memory dependency between these two access scopes applied to all of memory. That's using a VK memory barrier structure. Buffer memory barriers say create a memory dependency between these two access scopes applied to this range of memory. These are more fine-grained. They can also transfer ownership of a buffer between queues. These are represented using a VK buffer memory barrier structure. Unless you need to do a queue ownership transfer, using memory barrier instead is fine. Image memory barriers, same thing applied to a sub-resource range of an image. That's more complex than a linear range of memory. Right. Image layout transitions, image layouts is also part of that. On the current NVIDIA GPU driver, there's currently no benefit from using buffer memory barriers over regular memory barriers. So using the fine-grained does not have memory. This is 6 or 7 years ago, so I don't know if that's still the case or not. I think it is more of that now. When it comes to image memory barriers, which are discussed in the extras, okay. Applications should use as few barriers as possible, since this causes the GPU flush of the pipeline. So don't do it. You don't have to. So since this pipeline barrier is really about cache validation, if one's worked with multi-threading in C++, you might be familiar with how caches sometimes need to be considered when sharing information between threads. Issue is similar, except between the CPU and GPU. Instead of 2 threads, they both have caches. Simplified diagram looks like that. Later, with VKQwait idle, should make sure that the GPU writes are flushed to each GPU's VRAM. Won't necessarily flush the writes to the top right cache, which would make the memory available to the CPU. Make so that you can see the correctly updated contents. Buffer barrier tells the GPU to flush the writes to the top right cache, making the memory available to the CPU. Now that we more precisely say what setting the host coherent bit flag means, makes it so that these writes are also automatically made visible to the CPU through the invalidation of the cache. Now that the system made the memory available and visible, the CPU can read it correctly. In practice, the driver implementation might always flush the right caches, so the application might work without this pipeline barrier. This is more image pipeline barriers in the extras. Some more resources for readers interested in learning more about pipeline barriers. Yeah, a lot of the concepts are useful in other forms of Vulkan synchronization. So execution of memory dependencies in the specification. Also synchronization and cache control. Yet another blog about Vulkan synchronization. So adding the command buffer, queue submission, forwarding the GPU data back, going to make sure the GPU is finished. VKQwait idle. Just, it makes the CPU wait until the GPU has finished all the work in a queue. Okay, freeing command buffers and pools. Make sure to free the command buffer. Okay, destroy the command pool. Then the readback should show the updated contents. So last two chapters, we saw allocation of GPU memory, buffers representing an image, GPU and CPU data mapping, creating a command buffer with command pool, recording and submitting command buffer with a VK command fill command. Okay, so we want to stop here, or is that the chapter 5?
Yeah, let's stop here.